We are Wang Yiyan, Yu Kuanheng, Chen Zhehuan from Peking University. Now we are presenting our jobs on Chinese standard Mahjong AI based on the searching algorithms with traditional evaluation functions. As a popular competitive Chinese entertainment in the world, Mahjong has a history of more than 2,000 years. A number of series have been presented to explore its origin or probability of and game theory. It's because of its interest and challenge on thinking that educators usually apply it to courses as an excellent as its example. Our research, which is the improvement of our course project, was done on Chinese standard Mahjong, one of the commonest rules of Mahjong. To begin with, the glossary list is shown to give a clear account of some concepts mentioned in the following descriptions of our research. To solve this kind of problem, searching is one of the commonest methods. However, as the numerous states can never be completely assessed in quite limited times, an effective evaluation function is required to be carefully designed. Let ES we use in our program is calculated using PS and LHTS. It's obviously that ES is positively correlated to ABS, PS, while negatively correlated to LHTS. With the assistance of the evaluation function, many decisions are easy to make. First, we can assess the weight coefficients of expectations of the current patterns within a game. For a current pattern S, calculate the probability of achieving each pattern in PS. Firstly, to simplify the model, we assume that all tiles will be drawn at the same possibility of P, and claim at a possibility of 3P when playing a coin because of discarding of the other three players, or P when choosing from the player on the left hand. Secondly, we count the remaining number of useful tiles A as RA, then multiply it to the result. Thirdly, consider that we can claim tiles only when we have already held two tiles in a group. Therefore, possibility of claiming a useful tile is actually lower than we calculate above. We define some suitable parameters presenting the possibility of forming a group by pulling and showing when locking two or three tiles. In addition, we take the special from 7 pairs into consideration. Complexity of combinations influence that the average possibility of reaching a winning hand decreases so we redefined the possibility of drawing a tile as P7. Last, make a product of the possibility of all useful tiles for every winning pattern and sum them over. The output ES is used as the expectations or weight coefficient of the current pattern. We can also assess the importance of each tile when needed to discard a tile. For every tile A enumerated in hand, calculate E(S)(A). The larger E(S)(A) is, the less important F for the current state is. Obviously, we choose as satisfying E(S)(A) equal to the minimum of E(S)(A) as the discarding return. We can also assess the operations of gambler-komqaq at a moment. For the climbing operation OPA, calculate ES plus OPA and judge whether ES plus OPA is greater than ES or not. If so, accept the climb, ignore otherwise. The major work of the program is to generate all winning plans PS for the pattern as we hope every moment. It takes our program majority of executing times. The searching begins with the groups formed by climbing operations in the current pattern as the initial state. Then we apply the functions df as triplet to search the triplets, then df as sequence to search the sequence in order to produce a winning pattern. The greedy idea of this searching order assists improving efficiency and accuracy. Once reaching a possible winning pattern, we use the function judgeWho to judge whether the point of the pattern is not less than 8. If so, we successfully get a winning hand, T. Then WHT ST is easy to calculate and LHT and PS are updated. The total number of states has a theoretical upper bound of 1.5 times a billion, which is quite unsettlable because the function judgeWho runs as slowly as crawling. We hope to control the state's number under a level of 100,000, which is what we mainly do in our program introducing the following. As one of the commonest optimizations used in searching algorithms, planning does work efficiently. First, as a dynamic calculation of LWTSD using the LHTS to pronounce while searching is available. Then we limit LHTSD to 6 while searching. The restrict proves to be reasonable. The upper bound of LHTS, which is actually 7, is easy to know because of the existence of found 7 pairs. Using simple statistics, we know that the possibility of a pattern's absence of pairs is less than 1%. Then we can design a DP algorithm to work out the possibility of a pattern whose LHTS is more than 6 equal to 7 as less than 0.5%. For this part of 0.5%, we decide to discard win tiles or cardinal tiles first for the efficiency of winning in case the program hasn't found a winning hand yet. In the actual running, we find that program can produce all the winning hands in no more than 2 seconds. In less than 1 second, if LHT is less than 6. That's what proves that we managed to step to our goal. The remaining problem is to resolve the time exceeding when LHTS equal to 6. In view of the short distance of our purpose, expectations analysis which may do harm to the accuracy seems unnecessary. So it occurs to us that not only when needed to respond to the information we can do some researching, but also when there is little need for response. In this way, we make as full use of as possible of all resources. We upload the current HTS and PS to the platform so that we can download them the next executing time. If we haven't completed the current searching yet, when time is existing, we will upload the incomplete searching path as well and use the combination of last uploaded and the current HTS and PS to calculate ES. Considering that the last and the current result differ slightly, we are confident that this method works. With the optimizations above, our program manages to achieving our goal. To keep the robustness of the program, we should adjust the related parameters through observing the booth behavior in a real context. After some jobs, the file parameters are listed in the following. That's our entire work. Thank you for listening.